When you're looking at data analysis, a frequent term you might encounter is the distribution of the data. This is a statistical way of simply talking about how the data are arranged. Often you will look for a mathematical formula that is going to describe this distribution, but before you even get to that, you can learn a lot about your data just from a visual inspection of the distribution. Understanding the distribution is also very important if you want to know if certain tools or models make sense to use on a given data set, or if they just are not appropriate for that data. Often we visualize this distribution by plotting the data as a histogram. You can do this using actual value counts of the data, or you can normalize the data. Either way, you can see how they relate to each other. Now, it's also clear that the more data you have, the easier it will be to see those patterns and to really understand if the data you have are representative of the true population you are dealing with or are skewed in some way. One type of distribution is a continuous distribution. This is a distribution which any value within the given range that's applicable is possible. For example, we can look at the population of adults and their height. Now, a person can be any height within reason. Someone can't be a negative height, they can't be zero height, but you can be 4 foot, 4'2", 5 foot, 5'2 3/4", and so on. There's not set intervals at which your height is measured. Now, some people are taller, others are shorter, and the average height of a group of people may not describe any specific person, but it's an estimate of what you might expect if you're talking about that group as a whole. Now, if we look at the data shown here that we pulled from Our World in Data, a website where you can gather various data sets, we can see that when grouping by gender, men are, in general, taller than women. That doesn't mean that all men are taller than all women, but on average, we see a difference. Now, the other thing you can notice in this distribution of data are that you have a very symmetric shape to these heights. Around the average, you have about equal numbers that are taller and shorter. You have about equal spacing on these extremes. And this is the shape of a normal or Gaussian distribution. On the other hand, if we look at the distribution of mountain heights as pulled from Wikipedia, you can see that there is not an equal number of data on each side of an average. Rather, there's a couple different peaks, one centered kind of around 3,500 meters. You have a nice tall peak just over 4,000 meters, and then you've got another peak around 7,000 meters. So we definitely do not have normal distribution here. The other thing that this leads us to look at is that very low height area. The shortest mountain on this list was at 12 feet in elevation. Now, how does a 12-foot thing get declared to be a mountain and other 12-foot things get called hills? Oh, that's a criteria someone had to choose. And how that is chosen is going to really affect the data that are in that small height region and can drastically change that distribution. On the other hand, at the high side of the distribution, on Earth we don't have anything taller than Mount Everest. You could bring in data from other planets, but those are a different data set because they might come from different processes. So it might be a different population. So this data has to be treated very differently than your normally distributed data. Data can also be distributed in a non-continuous fashion. So you might think of, for example, the number of people it takes to screw in a light bulb. You can only have integers of people. You can't have half a person. This is a very different scenario because you just can't have any number, and so you have to treat this statistically differently. We show this here in this example of data that were taken from an internet repository of light bulb jokes, and you can see that you have a very skewed data set. Most of the answers are grouped around very low numbers, but some go very high. And so this is going to need to be treated very differently than your continuous sets of data, whether they are normal or not. So in conclusion, you simply want to make sure that you take a chance to look at your data that are there. What your data look like can really drive how you want to approach a problem. They may mean that certain things you want to try just aren't valid. They may mean that some things are overkill because the answer is very simple and straightforward. They may also show you that some things just aren't working. For example, you may have a value that's just physically impossible. If you have a bunch of heights of people and you see someone at a group of people at -1 feet, well, it tells you that something went wrong when those data were gathered. And so you can easily know that they should be discarded and not included in a general analysis. So it's simple and straightforward, but just take a moment to look at your data before rushing forward into an analysis.